Hello, welcome to session number 2 in the series Electrodynamics. My name is Anurag Nigam, and today let me just recollect. Last time we have seen different simulators from different companies, and today I'm going to start with Momentum and EM Pro, and I'm going to look into a method of moment, right? And when it comes to method of moment, my word starts from here with R.F. Harrington, and this is a seminal work on method of moments, and this is available online. This is out of print right now. So if you were going to write method of moment, you should refer to this book to start with. So in this book they cover the actual algorithm for method of moments, right? And they cover the entire theory of solving the Maxwell's equations, and then from there on computing the voltages and currents in sheet of metal, right? So this R.F. Harrington, right, is the guy to start with if you want to learn writing method of moments, and this will give you a lot of insight into what the simulator is actually doing, right? So this is R.F. Harrington. Then my work also starts with the guy called Yee, right? In 1966 he gave the Yee cell, right? So let me show you a Yee cell, and later we will go through this document later on, so don't worry about it. So my work started from here, so that's a Yee cell, right? So in FDTD, okay, this is the basic cuboidal element, right? And then if you see here, the space steps are half space steps and time steps are half time steps, right? And then there are Maxwell's equations which are discretized in space, and then they are discretized in time also, right? So you see that this is what is being written inside your XFDTD, or this is being written inside your EM Pro FDTD, or any FDTD in the world. That's what it is, right? And the current factor which I was talking about is this diagonal element, right? Okay, this is going to give you dispersion, so this is called current factor S, right? And your sizing of a grid should be such that this is in tolerance, right? So then the computation will be stable, and then there are perfectly matched layers and stuff like that. So my work also starts with this person. Okay, so this person is Alan Teflov, right? And you can find his book. So let me just show you over here. Okay, so this is the book, okay, where it starts from, in the public domain, with Alan Teflov. And another lady is Susan Hagnes, 1975. This is where this comes from. But before that, far before that, in the defense records, this comes from Yee in 1966. Okay, so this is where the stuffs is born. Okay, so we use various tools, but then we don't look at the algorithm. We don't look at why we are using a certain boundary condition and why not the other boundary condition. So this will come from when you study this book. You can get online this book, right, which discusses the algorithm, which I have discussed in my own text, right? So in my own text, it's over here, and it is these equations which we write in MATLAB, or you can write it in C to solve your 3D objects. Okay, so this was for the history. Now going back to method of moments, right? So I can basically close this. You can find these online, these books. Okay, so now the first thing is, Okay, the first thing is using these applications. So the question is, what is the use of, so let me see if I'm recording. Okay, so now the question you should ask is, why EM simulation? What's its use? So most of the designers, right, they start designing integrated circuits from here. They start with a transistor, then they go to tune this transistor, and by the time they have spent few days, they would reach to something like a 3-stage kind of thing, right? So let me just show you that over here. Okay, so they reach somewhere here where they have got a pre-driver which is tuned, then there is a interstage 1, right? Then there is a interstage, then there is a driver stage, and then there is a interstage 2, and then there is a power stage. Okay, so you are tuning individual transistors, and then you are cascading this, and this is also a art, right? So what I'm doing here is where the work of a designer ends, a normal designer, but my work starts from here. Okay, so my world starts from the imagination of what the final product is going to be. Okay, so this you are looking at is a triquint PA for Wi-Fi application, and this PA is a 3-stage PA which is sitting inside its own QFN. Okay, and I'll remove the lid so that you can see inside. Okay, so here I have thrown out all the transistors. All that's remaining are the pads for the input. So these 2 pads are for the input, these 2 pads are for the output, and if you see, they are ground reference to via here, so that's a via, right? So my world starts with imagining what a ground would look like. Okay, and the circuit can be built in between, right? Okay, so my real world starts from this box, okay, which is 3mm by 3mm, and this sits on a Rogers laminate which you see here, right? And then this laminate is sitting on bunch of vias, because that's how your ground comes in and that's how your heat goes out. Okay, so as a designer I start thinking from here. Okay, so let's go to the substrate and let's make it invisible. Okay, so what do you see? You see a bunch of vias which are sitting under the QFN. Okay, so this is called a quadrature phase no lead package, or QFN, and I have removed the lid of it. So you are seeing it's kind of a hollow box with a central pedestal which you see here, and then there are pins which are like 16 pins here, right? So now this is done in a HTCC process. This is ceramic. Okay, this can be plastic also, right? So my work starts from these parasitics. So if you see, the bond wires gives in rise to inductance, and then the pads give rise to capacitance here, and then there are capacitance all along the length of the wire, and then the terminating pad also sees a capacitance with respect to ground underneath. So that's the ground underneath, right? So that's the ground underneath, and this output also sees a capacitance. So you have a CLC structure here on the input, and similarly you have a CLC structure on the output. And let me tell you, this C which is on the board side, it is of the order of 30 to 40 femto, because the ground is almost 10 mil away or 5 mil away, right? While the capacitance here basically is going to be much larger for this bond pad, right? Because this bond pad is sitting on a substrate which is only 100 micron or 4 mil. So this capacitance is dominant, right? So there are C on the pad, which is a board pad. So what you see here, this QFN is sitting on a board, right? And then you have got this line which comes in for the input and the line which goes out as the output, right? And then there is a bias pad for the biasing also. You do not have to model all the biasing, because you might have a good decoupling on this, but it may not be that the decoupling may not be good, it may be part of tuning. Then the bypass becomes important, and then this portion in RF performance of any gain device becomes important, right? So I guess you understand what this is. And now if you look at ground, so I will even switch off this box. Okay, so let's switch off this box. Okay, so now you see that this is the kind of structure which is a part of QFN. So this is a pin in the QFN, right? And this pin to which the bond wire comes, so all these pins are QFN pins. And then you see that this is the via of the board, but then the QFN has a pedestal, okay, which may be solid. So in this case this pedestal is solid, right? So that ground comes from there, from the central pedestal. Okay, so that's the central pedestal from where the ground comes in into this chip, right? And if this is gallium arsenide or nitride, ground is over there, and then it comes out up to the chip through a via. So let me just turn on this one. What you see is going to be gallium arsenide or gallium nitride, or maybe silicon or silicon germanium, or it can be silicon carbide, right? So let me switch off this also. Okay, so now what you see is these vias, which are substrate vias. Now these substrate vias come up, right, and bring the ground onto the chip, right? So everything is going to be relative to this ground. Okay, and the ground is not 0 volts. The ground is distributed. Now everything which you see over here, if I turn on all the pins, for example, right, turn off all the pins. So I'm going to turn them off. Okay, and some pins are left, so I'll turn them off also. So there is a board in. I don't want to turn off that. So I'm going to turn this off. Okay, and still some pins are left, is it? What is this one? Okay, so maybe this is, okay, this is a coplanar ground pin. Okay, so what you are looking at now is the ground. The ground comes for the terminal, the ground comes from here, and this is a transmission line, and this is a board, right? So this is the ground, and for a chip the ground comes from the via onto the lower pedestal of the QFN, and then it goes up through substrate via onto as a coplanar structure over here. You can have ground routing on here, right? So I guess you understand this is what EM simulation is all about. Okay, so this is a 3D simulation in EM Pro of a QFN package. So let me set all visible. So over here, okay, now this portion what you see is your pads on the chip, right? So these are the pads on the chip, and what you see over here is a piecewise linear approximation of a bond wire, which is edge bond. You can do a ball bond also on this. But what I'm trying to explain, if I'm a product designer, okay, my world really starts over, you know, this kind of stuff where, you know, I worry about packaging in the start. I worry about how this is going to be tested in the start if I am a product designer. Okay, so everyone has to be a product designer. Okay, what you study as these Okay, let me see what happened. Okay, let me close this and open this again. Okay, so don't worry about that. So the thing to look at is what EM simulation does for a circuit designer. So that's what I'm trying to show you, the applications. Let me just start that. Okay. Okay, let it open. Okay, so I guess you got the idea. When you design an IC circuit, the IC is basically the chip which is sitting inside on a QFN. The IC is not the plastic package or the ceramic package. It is the part of the wafer which is diced out, and it is wire bonded or soldered onto a pedestal. That's the chip. That's the integrated chip. And whatever you see as a plastic and pins, that's a package, right? So a designer thinks of a package at high frequency first, rather than thinking of the circuit first, because without that you might do a fantastic design over here. Okay, you might do a fantastic design in this sense. Let me show you. Yeah, you can do a fantastic design in this sense, right? But then this might not work. Okay, this might not work unless you involve the package also into the design, right? So the package has to be included in the design, and so the simulation has to involve this package, because all your matching is dependent on ground, because all the impedances are with relative to local grounds, not the 0 volts. So this becomes very important. So this was done in EM Pro as a QFN and then brought in as a component here, and that component basically goes into putting in V out and stuff like that, and VDD. And then there are 3 stages here: driver stage, pre-driver stage, driver stage, and power stage, right? And I will talk about stability when it comes to 3 stage. A lot depends on what's happening between the power stage and the pre-driver stage. So that's the bias or bias decoupling becomes important when you put 3 stages in an IC. Now what that IC which I showed you over here is sitting inside here in this box, which you see this one. And if you want to see what it exactly looks like, okay, so file, chapter 12. Oh, okay, what that IC looks like. Okay, so that's my notes. So that's the design, right? So that's the 3-stage design. Okay, so this is in 2.5, 2.4, 2.5 gigahertz, right? If I'm not wrong. Yeah, it has to be that band, 2.4 to 2.5 gigahertz. And that's the thing which you have seen, right? This IC goes inside. So basically for me it starts with interpreting this design of a QFN, right, in which this IC is going to sit, and this IC is going to be this IC is going to be like this. Okay, so basically here is the top view of the layout here, right? So if I do a width, okay, so that's the IC, and that's the 3-stage IC. So you can see RF out on one side. Okay, so here is the RF out on the right side. Okay, so that's RF out. Then there is a driver stage which is over here on the right hand side, and then there is a pre-driver stage which is on this side. So there are 3 stages in here, and there are bias decoupling networks on here, and then there are matchings on the output side, input side of each of these 3 transistors, right? And then these three transistors, there is a bias circuit. Okay, there is a bias network, okay, which sits here, and then there is an on-off switch here for switching off this for a standby mode, right? So this is a temperature compensated bias circuit, okay, which sits, I think, which sits in here. So it's a two-stage right now, so it's not a three-stage here, it's a two-stage here, right? And so I'm mixing the two designs here, so let's not mix that. What I was showing here is a 10 gigahertz design, so we will discuss that later on. So this is a 10 gigahertz. So let me see. Yeah, so I'm doing a sweep here, right? So this is a 10 gigahertz design here, right? So this is a different design. So this is a three-stage design. What I'm showing here on the QFN is a 2.4 to 2.5 gigahertz in a tri-quint PHEM process, right? So that design basically is a two-stage design, okay, which is over here. Okay, so this is a two-stage design, and this one is sitting on this FR4 board. So this is the profile of a board, right? So remember I told you that momentum is a planar, for planar circuits it's used, and PCBs can be done, but then this is the not a cross section, it's a profile. So the extent on left and right of this doesn't make any meaning. It's not a cross section of that board, it is a profile. So there is no meaning to going from left to right. Okay, there is no information from left to right, only there is a profile information here which says that I'm going to use a 10 mil board, 10 mil at the bottom, 20 mil at the in between, and 10 mil at the top, right? So that's what this board is, and that's the QFN. And then what is inside is a two-stage like this with a bias circuit. So in this case, in the layout, what you see is a two-stage. So this is between 4.4 and 4.5 gig, 2.4 and 2.5 gigahertz. So there is a power stage over here, there is a driver stage over here, and this is a biasing circuit. This is a VT referenced. This is not exactly VT reference because this is temperature compensated, flat across temperature. You can do a pseudo PTAT or pseudo band gap. That kind of bias circuit is over here, and then there are matching networks, and then there are ESDs, right? On all the pads, all the important pads, you will find ESD. Okay, so that kind of layout you are supposed to do in momentum. So this was done in momentum, right? Okay, so I will search for the project and show you live, but that's what it is. Okay, so you got an idea where you need a 3D simulator. You need a 3D simulator in case of packaging. You see a lot of 3D structures, right? While here you see 2D structures which are planar, right? Where they are in different layers, but still they are planar. So basically when you draw, you are seeing the top view and you are drawing on a certain layer. Okay, so all these red ones, these are capacitors. These are all capacitors, right? And then these coils, these are your inductors, rectangular inductors, which are stacked inductors, right? So inductors, capacitors, and then you have got these PHEM transistors, right? And then these PHEM transistors are grounded with these grounds, and these ground locations are fixed, okay, because I simulated them that way, right? So that ground is one solid ground from the board up to the chip, right? Okay, so this is what goes into IC design or MMIC design, right? And you can understand the significance of the simulator, right? The EM simulator. Okay, you can understand the significance of EM simulator. So now I'm going to also show you a 9.5 to 10.5 gigahertz X band PA. right? So this is a X-band PA. Okay, so of course you will read about in basic books all matching and all that stuff, but you see this is bias decoupling. There are various forms of bias decoupling. Now here you see on the left hand side, this is a EM simulation of the decoupling. So it's not just the circuit which I use to make sure and the RF is decoupled from DC. Okay, it's the layout where I make sure that it is decoupling is good, but also all the parasitics at other frequencies, because what happens is the compression characteristics depend on all the odd harmonics which are generated and how you handle them. So what is this decoupling looking at other frequencies other than the fundamental? At the fundamental it looks like an open circuit for RF. Okay, from the RF side it looks like an open circuit, right? And you can see any kind, it can be just an inductor and a bypass cap, it can be an inductor capacitor and a bypass cap, it can be a quarter wave stub. So this radial stub establishes the ground or a short at this right hand side, which is transformed to open by a quarter wave, right? So this is, again, you have to do EM simulation on chip. Okay, whichever form of decoupling it is there, that EM simulation has to be done, and then you have to make sure that looks like open, and then you put that EM simulation in your circuit simulation here, and then you are going to do the tuning, or you are going to stabilize the transistor and then do the tuning, right? So once it is tuned, you are going to do a large signal tuning and stuff like that. But then you do this for pre-driver, driver and power amplifier till you get a 2-stage or a 3-stage you are looking for a given gain, and then you also going to verify it is stable on the last signal. So that's the stability on the last signal on the right side, right? And this is the IC substrate, what it looks like. Now what I'm using here is a demo kit, and the demo kit is provided to you by Keysight. Okay, so the demo kit is provided to you by Keysight. So let's open something like this one, right? So if you see on the left hand side this palette, so this demo kit is provided to you, and what can you do with this? Okay, so to see what you can do with this, I will refer to the presentation here. So what am I doing? I am constructing, first of all I constructed the circuit, but then your work doesn't finish here. You have to construct the layout which behaves the same. So then I will go matching section by section, and in other videos you can see how I do these section by section. And then finally, when I have done all the stages, I arrive at a 3-stage. So that's a 3-stage layout. Okay, so here this is 9.5 to 10.5 gigahertz. This is the layout where the leftmost is the pre-driver, a driver and a power stage, and interstage matchings are in between, and then input and output matchings are there. Then this is placed inside again some kind of a QFN, and the capacitance of pads and the inductance of bond wires have to be a proper transition design at high frequency. So this is across power what I'm doing, but what is important to know is that this demo kit provides you everything. Okay, now what you are looking here is the temperature profile. Okay, so what other thing this momentum they have included in Keysight is what is called electrothermal simulation. So you can look at the temperature profile and you can see how the heat is being taken out. So you are designing not for just the electrical parasitics, but you are also designing for the heat flow, right? So that's how your PA is to be designed, right? So let's see what kind of power output do I get on this one. Output power, it's around half a watt. So this is a half watt PA. So this is a 3-stage. This is a 3-stage half watt PA using the demo kit in ADS, and this is goes up to thermal simulation. So let's see in ADS what this thermal simulation is. So thermal. Okay, but then there is a way to visualize thermal. right? Hang on a second. Yeah, but I want to look at the thermal view of it. Electrothermal simulation. So let me put you on a pause. Let me open it and then show you. Okay, so it seems like they have moved that licensing to a separate bundle, W5900 or W5901E, right? So they have named this product as Heatwave, right? And that's why I don't have the thermal simulation license with this ADS, which is a university version, right? So this is a donation copy for Government Engineering College where I don't have the thermal simulator in it. Okay, so I cannot show you that, but all I can show you is that this design was done on a borrowed license and which had a thermal simulator, and you can look at the thermal profiles and you can see the circuit with with the thermal effect and without the thermal effect. You can see, you know, the compression characteristics, and you can see how is the heat basically being taken out of a PA, right? So all that stuff you can see in that if you had a bundle, license bundle which supports Heatwave, right? So anyways, so this presentation was done for Keysight only long back, where I borrowed a license to do this thermal simulation. So what I'm trying to say is that this momentum which is there in ADS not only supports EM simulation, but it also supports electrothermal simulation, right? So let's close this workspace. Our focus of the day today is going to be momentum. Now, before even I start, that's why I'm trying to give you application view of it. So momentum can be used not only for this EM simulations for ICs. So for example, for over here, this is a gallium arsenide process, and then this is a two metal process, metal 1 and metal 2, and then you can see there is a MIM capacitor, there is a p-HEMT here with the air bridge, right? And then this is a capacitor with the air bridge. Similarly, there can be, you know, inductor with the air bridge and stuff like that, right? So, and these are your DRC rules. So you work with this kind of a substrate, and you can do passives on top of this gallium arsenide. Okay, so if you look at, yeah, so that's what EM simulation is going to be for ICs. Now for laminates, right? So let's put that aside. For laminates, you have got various options. Okay, one is called the LTCC, or low temperature co-fired, okay, ceramic. So this is LTCC. Now here LTCC process is available from various manufacturers of green tape, what they call green tape. So this is Ferro green tape, and then it is a silver based, all silver based metallization. So that is why it is called Ferro AS system, right? AS stands for silver, right? So this is capable of going up to 100 gigahertz. So you can design your boards using LTCC. And here you can see this LTCC basically comes as a semi solid green tapes, right? And these green tapes are basically, there are different steps involved here. So here you can see these are provided in these reels, okay, and in these reels there is a plastic backing on these tapes, right? So you do not remove the backing. What you do is you get this tape, and then you cut it into square blocks, and in this square blocks, okay, so this is like a semi-solid, right? It's light green colored. So when you cure it, it is going to be milky white, right? And then the corners you punch in holes where the posts go, right? If you see this guy, okay, so this is going to be applied onto a metal frame, and then metal frame basically has got 4 poles on the corners, and then this LTCC square block is going to have 4 holes which are punched, and then you can slide that through those 4 poles, and then you can put one layer over the other, and then you can exert certain pressure to when you have applied them, and then you can put it into an oven for curing it. So you do not remove the tape, the backing, the plastic backing, till you have done the entire printing, punching and everything, right? And metallization is done through screen printing. Again, for that there are silver based pastes, and then you do the screen printing of these circuits, right? So you can stack those one on top of the others, which eventually when they are fired, they are going to shrink. They are going to shrink along X and Y, which says 15.3%. So when you do the simulation, you are simulating on a contracted design. But when you send it for fabrication, you expand X and Y by 15.3%, and your Z basically is going to be taken care of automatically. So, but then in your simulation, VRs are going to be taller. It's going to be shorter. While in case of the tape, they are going to be taller because there is going to be a 24% shrinkage on the Z direction, right? So when you do LTCC, there is a shrinking involved in X and Y and Z direction. So you should use the post firing dimensions for simulations, right? So for example, for over here, there are different stacks of these. This is a cross section, right? So there are different stacks, and then you have got punching holes. You can fill in with the paste, and that makes a via, right? And then you can screen print the circuits, right? So basically it will be like a multi-layer stack up of LTCC, right? And in that you can also form cavities, like if you want to do resonant structures and all that, right? So you can also do cavities there. You can also do resistive material here to make resistances. Okay, you can make inductors and capacitors. So this kind of stuff you can do with LTCC here, right? Okay, so once it is done, applying all the different layers, then it looks something like this. So these are stacked on one on top of the other, and this conveyor belt takes it through the oven, right? And when they come out on the oven, they are cured. Okay, now in some cases you might have to flip these, because what happens is if the different layers are not loaded uniformly with the metal paint, then the shrinkage would differ on different layers and it may buckle up, right? So in that case, in some cases you flip this entire assembly, okay, to cure it uniformly. Okay, so some of the processes don't need that flipping, but some would need flipping. Second thing is when you do LTCC layouts on different layers, the density of metal structures should be uniform. If it is not uniform, put the fill metal areas, right, so as to make the density of metal uniform on different layers, so that when you cure it, it doesn't buckle up, right? So that's the thing which you have to take the caution. Okay, so once you do the co-firing, okay, this might look like that, but then on top of it you can put metal frames, pins and stuff like that, right, which adhere to the top metal using another silver based paste kind of material which is cured, right? So you can do a LTCC for modules, right, which is system in a module kind of thing. Again, to simulate all this, you need EM simulation, right? Okay, so EM simulation has that application also. So your laminate can be a LTCC, or it can be HTCC, as in case of QFN you have seen. Okay, now another thing is you might do layouts on these boards. Okay, so these boards, like for example from Rogers. Okay, so this is a 4000 series, right? And you can find different laminate which suit your application. So for example, this 4000 series is close to your FR4 with what you call a dielectric constant. So what is important here for any material, okay, which is a dielectric, so the properties of a dielectric material, that's what you need when you do simulation. Properties of dielectric material. Okay, so now let's list them. Okay, so A, you need something called dielectric constant. Dielectric constant. Okay, now let me tell you what is dielectric constant. So let me insert equation. Okay, so what you call epsilon, right? Okay, what you call epsilon is basically epsilon r into epsilon 0. Okay, so this is epsilon r. Let me just write it. So this is epsilon r into epsilon 0. So epsilon 0 is for the free space, which is 8.854 into 10 raised to minus 12 farad per meter, right? So that is going to be epsilon 0. So just one second, bear with me. Okay, so you have got epsilon 0. Okay, so you know what is epsilon 0 for your free space. Now this epsilon r, okay, this epsilon r is a complex number. Okay, so that epsilon r is basically can be written as equal to epsilon r dash. So I can write this as, let me just delete this. So this can be written as epsilon dash. So sorry, mistake again. Okay, so it will be epsilon r dash, again a mistake. Where is it? Okay, epsilon r dash and minus j. So this is a complex part. Epsilon r double dash. Epsilon r double dash. Okay. Okay, so now whatever you specify as epsilon r dash. Okay, so I'm going to list an example of some epsilon r dash. Control C, Control V. Okay, so this is equal to 4.2. Okay, to 4.8 for FR4. This is fire resistant grade 4. So we call this as FR4. Okay, so for FR4 you have got this. Then you have this Rogers material, right? Again, which is equivalent to FR4, right? So if you look at Rogers material here, okay, so this 4000 series, you have dielectric constant which is close to 4.2, right? So it is over here 3.38, you have 3.48, right? So this is 4350B, then this is 4360G, which is 6.5 here, this dielectric, right? So what you're seeing is there are different materials with different dielectric constants in this 4000 series. Okay, and similar, so this is for the fire resistance series, which is the cheapest from Rogers. Okay, the other one is this Duroid, which is a high frequency laminate. And when we say high frequency laminate, it means that we are talking about loss, dielectric loss. So you refer to my series on microwave and millimeter wave circuit, then you will know what's a dielectric loss. So here what's happening is there is another. So let's say we are talking about some more. Let's say RT Duroid 5880. Okay, so in this case epsilon r dash is 2 point something, right? So you can go to data sheet, okay, of Rogers, and where you will have an idea about what this is. So RT Duroid 5880, it's 2.2 is the dielectric, right? And so 2.2 is the dielectric. Okay, Similarly, if you want to design something high power, then you have to use thermoplastic kind of stuff with fillers. So that is, for example, TMM10I. Okay, again this is a Rogers only, TMM10I. Okay, for here the dielectric constant is going to be let me see, 9 point something, right? Okay, so this is that 9.8, right? 9.8. Okay, so what is the significance of this dielectric constant? I'll tell you. 9.8. Okay, higher the dielectric constant, more dense are the electric fields in the substrate, right? So that's how you can put it. Okay, so if your electric fields are going to ground from a signal, then they are going to be dense if epsilon r dash is high, and that also means that your structures are going to be smaller, because then the wavelength is going to be smaller, because you know what is going to be velocity is equal to wavelength into frequency, right? So wavelength is equal to velocity by frequency. That velocity is going to be c in open space, but then c divided by square root of mu r epsilon r, right? And if epsilon r is higher than 1, then the wavelengths are going to be shorter in high dielectric constant material, right? So that's why if you choose a high dielectric constant material, then the wavelengths are going to be shorter. But then there is a drawback here. The drawback here is that the velocity of propagation is going to be 1 over square root of mu epsilon. So mu is 1 into 4.7 into 10 raised to 4 pi into 10 raised to minus 7, okay, Henry per meter. So that would be mu r 1, mu 0 as 4 pi into 10 raised to minus 7. Then you have got epsilon. Epsilon would be epsilon r into epsilon 0. Epsilon 0 is 8.45 into 10 raised to minus 12 farad per meter. Epsilon r is going to be higher than 1, for example. Then the velocity, which is c over square root of mu epsilon, is going to go down. So velocity of propagation goes down if you choose a larger dielectric constant. So you understand the significance of dielectric constant. While the imaginary part, right? So this imaginary part can be expressed as loss tangent. So what I mean by loss tangent is, let me write the formula for loss tangent. Okay. Okay, so I can say tan delta. Okay, so delta is, so I'm very poor at this, tan delta, and this is called loss tangent, which is inverse of or reciprocal of dissipation factor. Okay, so tan delta is going to be equal to sigma. Sigma is the conductivity of the substrate. Sigma plus omega. Omega is the frequency in radians per second, right? So that would be, where is omega? Omega epsilon r double dash divided by, so basically it will be this divided by omega r this single dash. Okay, so a loss tangent is specified like this. Okay, so this will be the second thing, which is loss tangent. Okay, so the loss tangent is defined like this. Now if you look at substrates which are conductive, for example silicon or silicon germanium or silicon carbide, right? So these are going to be conductive substrates, where conductivity is going to be 6.67 Siemens per meter, right? So that will be conductivity in that case. So in case of conductive substrate, so I can write here conductive substrate like silicon germanium and silicon carbide. Okay, so in case of conductive substrates, sigma is dominant while omega epsilon double dash is not dominant. So in that case, the loss tangent would be given by this. So I can delete this portion. So this will be your loss tangent. Okay, so usually conductive substrates in ADS are specified as epsilon r dash and sigma. So you do not go to specify the loss tangent. Now in case of insulating substrates like gallium arsenide or gallium nitride, okay, so these are insulating substrates. Okay, in case of insulating substrate, sigma is basically close to 0. So then the substrate becomes, so now you can see here the substrate is frequency dependent. Okay, so this is in case of okay, so this is in case of your silicon germanium. Here, once you cancel this portion, you also cancel this portion. So you see that the substrate is not frequency dependent, so it's not dispersive. So then substrate can be two types: dispersive substrates and non-dispersive substrates, right? So in case of EM Pro or ADS or momentum, you can model them as things with loss tangent or things with sigma. Okay, so you have a choice to do that. Okay, so now some typical numbers you can see again here from the website. Where is it? Okay, you see the loss tangent in case of here dielectric constant. What about loss tangent? Thermal. Where is the loss tangent? Okay, so they are specifying loss tangent is this, isn't it? Yeah. Okay, now why this TMM 10I is used? So if you have, it has very low thermal coefficient of expansion. Okay, so if you have temperatures rising to high values, you want a design which has low thermal coefficient of expansion. That's why you are going to use a TMM 10I kind of a substrate, right? So if you have a large high power stuff, you will be using this kind of substrate. Now this kind of substrate, the dissipation factor is very low. Okay, so you can see this is 0.0009. Okay, and in this case 0.0012. So you can see 5880 has 0.0009. So that's your loss tangent in case of RT Duroid 5880. So this is very good for loss considerations. Now if you look at this one, the loss tangent is not going to be so good. Okay, it is going to be again it shows 0.002, but it should be like 0.2 or 0.3 in FR4. Okay, so this is a lower loss tangent material from Rogers, but the normal PCB which you get, which is FR4, loss tangent is like 0.02, right, or 0.02 or 3 or something like that. So that's going to be a lossy substrate. So at high frequencies you are going to see a lot of loss here. Okay, so till now what I have been showing is the materials which you use in ADS, right, in momentum. So let me see where we are in terms of time. We have taken 54 minutes. So I'm going to stop here actually, and from the next from the next session, I'm going to start designing first on LTCC, and then I'll design various passives on LTCC using momentum, and then I will validate this on EM Pro, in FEM simulation. So I'll do MOM and FEM. Now for the chips, IC chips, I'm going to start with a typical gallium arsenide process, right? And there I'm going to simulate passives and then various components you can make from those passives. So that's I'm going to do on momentum, okay, in ADS. Okay, and then as far as the boards are concerned, you can do RF boards. So I'll show you various transmission lines on the boards and how do you design a transition from a planar line like microstrip to a coaxial SMA connector, for example. So that transition has to be designed, okay, or it can be a planar line like a microstrip to a waveguide transition. So I'm going to cover that in EM Pro, not in case of not in momentum. So I'm going to stop here because I have taken a lot of time into applications, right? So, and I showed you practical example of packaging, right? So more is to come on the next session starting with momentum. So thanks a lot. Thank you very much.